Awesome. Alright folks, let's get this party started. Let me just reset my timer so I'm on time. How's everyone doing today? Excellent, so much energy, I love it. Alright folks, and now for something completely different. Who knows what's the origin of the name of the language, Python? Where does the name come from? No, it's not related to the snake, it's related to Monty Python, the UK comedy troupe. Right? So there's this comedy group from the 70s, I think, called Monty Python, and that's where the name comes from. Now, take a second to think about the fact that the world's most famous programming language is named after a silly comedy group. Alright? And now for something completely different. In Python's release notes, starting from Python 3.8, the release managers, so the humans behind making sure that Python, the new versions get released and you're able to download them, those folks started adding a section at the bottom of the release notes with a "and now for something completely different" section. In Python 3.8 and 3.9, Lucas Lange added transcripts of Monty Python sketches. In 3.10 and 3.11, Pablo Galindo Salgado added astrophysics facts. In 3.12, Thomas Wouters, I don't know, I'm not sure how to pronounce his surname, added poems. In 3.13 he took a break, and in 3.14, 3.14, Hugo van Kemenade added pi facts. Pi as in the mathematical constant, the thing you eat, and apparently there's a bird called magpie. So there were facts about those. I don't know what's coming in 3.15, but I'm sure this tradition will continue. And now for something completely different. I wanted to teach you about generators, which is something, if you do a lot of data work, it's probably something you don't use very often. And once I read this really good example of how to explain generators to folks in a book I read, but I forgot the book. And so when I was preparing this talk, I wanted to go and find the example because it was so good. I wanted to teach you folks with the best example possible. And so I wrote a little Python function to help me find the example. And this function is going to grab all of the Python books I own, so I can go through the books and look for the example, right? And so I'll initialize a list that's going to hold all of these books, and then I'm going to go through all of my bookshelves. I'm going to look at all of my books in those bookshelves, and then I'm going to check, is this book about Python? Because believe it or not, I do own books that are not about Python. It's kind of difficult to believe, right? But I do have books about other stuff. And if it is a book about Python, I'm going to add it to the list, and then my function returns all of my books. I grab those books, I sit at my desk, and I go through them looking for the example. Now the thing is, imagine that I was lucky and the example was right in the first book. I went through all of my bookshelves, I grabbed all of those books, I carried all of them to my desk only to find the example in the very first book. So I spent a lot of time grabbing books, picking up books I didn't need, right? Do we understand that? That's wasteful. So what I can do is, instead of creating a list with all of the books, she was not amused by the talk, so she left. Instead of going through all of the books, creating a list, I can do something smarter. I can be lazy about it. The keynote this morning said, a good programmer is a lazy programmer. And I can replace a couple of things. I can get rid of the list and use the keyword yield. And this makes all of the difference. So let's compare the two pieces of code side by side. Notice the differences. The structure of the function is the same. That's why it's grayed out. I removed the list. The list is gone. So I can also not return it because there's no list to return. And instead of appending to the list, I'm yielding the list. So what does this define on the right? Python books is not a function, a regular, quote-unquote regular function. It's a generator function. It generates values on demand. It's lazy. And this small change has an infinite potential upside. So by using generators in the right places, you can speed up your code, you can save memory by an undetermined factor. It's up to you to measure, but it can be potentially large. Like, what's the largest number you folks know? 42. It's not very large, but in the right place, a generator could speed up your code by 42, by a factor of 42. Does anyone know an integer larger than 42? 67? 67, is that the joke or? Right, so in the right place, you could speed up your code by a factor of 67. It's not always going to be a 67x speed up, of course not, but in the right places it could be. And now I want to talk about something completely different. Let's see if you folks know this Python saying. So if it walks like a duck, and if it floats like a duck, then it must be... No, not a duck, a witch. Right? So for the folks who don't get the joke and are not laughing, you need to go catch up on some Monty Python sketches. Remember the folks that gave the name to the Python programming language. But yeah, the usual Python saying is if it walks like a duck and if it quacks like a duck, then it must be a duck. And this is talking about duck typing, this concept in Python that says we don't really care about the class hierarchy of objects. That's not the important thing. The important thing is the behaviors that your classes and that your objects have. That's why you say if it quacks like a duck and it walks like a duck, it's close enough to be treated as a duck, even if it is not a duck, like if you look under the hood. So that's the idea. How can we understand this with more than just a duck? Well, let's talk about a lot of animals. When you think of animals, I know there's other categories, right? There's other, the taxonomy is larger, but we can think of mammals and fishes and birds. And when we think of mammals and fishes and birds, you don't say fishes, do you? One fish, two fish? You can say fishes? Or fish. Okay, so I can say either. So let's alternate to make it extra confusing. So when we think of mammals, we could think of bats and whales, and when we think of fish, I mean, there's plenty of fishes, right? But there's sharks and flying fish. And if you think of birds, you could think of penguins and ostriches and others, right? And now, if we think about the way these animals move, if you just think about mammals, I would say these are typically animals that are on the land. You know, they walk, they run. And if we think of fish, they typically swim and they dive. And if you think of birds, typically they fly. But then, of course, I handpick the examples on the right because bats, they probably can walk, but their typical way of moving around is by flying. And I've never seen a whale walk. Not sure if you did. And if you look at flying fish, they can also fly, even though they're fish. And surprisingly, penguins and ostriches, they don't fly. They just walk around and run around. Although penguin running might be something interesting to see. And penguins, they dive and they swim. So it's not useful to use the mammal, fish, and bird categories, these classes, as a way of specifying the way in which the animals move. That's not a good idea because it's going to break. Does that make sense? Okay, because as we saw, these different animals, they move around in different ways. So what you do is, instead of coding these behaviors into the class hierarchy, because that's not going to work, you specify it separately. You say that a walker is any animal that can walk or run. And run. And you can see bats are walkers, and penguins and ostriches, those are walkers, because they know how to walk and run. For swimmers, anything that can dive and swim is a swimmer. So you've got whales and sharks and flying fish and penguins. And you get these behaviors that are independent from the class hierarchy. Does that make any sense? Alright, because this is the idea of protocols. So if you've heard of protocols, this is what they are. And that was an example from biology, but where is duck typing in Python? Where can you find it? And even if you didn't know about it, you've been using it this whole time. What's an iterable? It's a question for you. So an iterable is any element you can go through. Who's used pandas recently? Actually not a lot of hands. Have you ever iterated through a pandas data frame? Yeah, shame on you, but you can, right? So you can. I mean, if it's up to you to do it or not. So a pandas data frame is an iterable. yeah. So but you can. So pandas data frame is an iterable. So our lists. What other iterables does Python have? Let's stick with built-ins for now. Dictionaries are iterable, actually in 3 different ways: keys, values, and items. So in one, you said one thing, and it's actually 3 of them. You kill 3 birds with 1 stone. Sorry? Sets are iterables. What else? Sorry? Tuples are iterables. What else? There's a couple of very strings. What did you say? Yeah, strings. All right. Ranges, folks. Come on. Generators also. Yeah. Let's stick to something simpler. Like when you open a file, can you iterate through the lines of the file? Files are iterables. Have you heard of zip and enumerate? Those are iterables. So we've listed together like 13, 14 different iterables. What do they all have in common? Other than the fact that they're iterables? Very little, right? They're inherently different. They're very different things, and yet they share this behavior. So for the purposes of a for loop, they all quack like a duck. This is the idea. And now for something completely different. Have you ever written a list comprehension? Say an expression that allows you to write a list in a more compact way. What elements does this squares list hold? What are the 10 elements inside? Can you describe them to me? In words, you don't have to list them out. What we're doing is we're taking the range of 10, which is going to give us integers from 0 to 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm really good at counting. And then for each of those numbers, for each n in the range, we're going to square it. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3, 4, 5, 6. All right? So we get the squares. It's a very compact way of building smaller, not in terms of length. It's a fairly useful way of building simpler lists instead of having to write down the full loop. I could give you a talk just on list comprehensions. There's a lot here. But this is the main idea. And if you replace the square brackets, the opening and closing square brackets, with parentheses, what do you get? No. That was no, you don't get 2. Well, that's a very reasonable guess. But you actually get something called a generator expression. Do you remember generators from earlier? The lazy thing where I was going through each book at a time? This is a convenient way of writing a lazy iterable. It's a generator, not a tuple. Alright? These are very useful, you know? List comprehensions, they're compact, they're nice, but they're eager. If you need something you can go through, but you don't need all of the values there immediately, you can use a generator expression. Why? Because it has an infinite potential upside. Remember that? It can be up to 67 times faster. Crazy. And now for something completely different. Exercise is good for you folks. Exercising is good for your body. It's going to help you age well. Even if you just want to faint after doing exercise. But it's good for you, you have to do it. And now for something completely different. Have you ever thought about the fact that whenever you have an if statement, your code has 2 different paths? That's literally what the if does. It can either go in or not. What does that mean? It means that if a program has 10 ifs, it has 1024 different paths. Isn't it crazy? Do you get what I'm saying? Like if you have 10 ifs, you can either go or not. So that's 2 options. And then times the 2 options of going in or out, in or out. So each if you use increases the complexity of your code. Okay, that's interesting. So let's think about the Zen of Python that says that flat is better than nested, among other guidelines. Sorry, by the way, have you ever taken a look at the Zen of Python? Have you seen? Who hasn't seen this before? Import this. So if you open the Python REPL, I got you. Don't worry, I got you. Where's the terminal? And now this goes here, and this goes. Can I? No. Let me think for a second. Okay, so I go here. I stop this. I want to stop my presentation, and now I make this large enough, and I move this over here. No, sorry, I keep hitting the Okay. It's the hoops I go through just for you folks. I better get a good round of applause in the end. No, you have to run Python first. So you open the Python REPL, or in a file also works, and you import this. This is the Zen of Python. It's a set of guidelines that were written like 3 decades ago. These are not rules you have to follow. They're just interesting guidelines to make you think about the way the code is structured. And somewhere in here, the fifth sentence says flat is better than nested. So that's what we're going to think about for a second. So now let me go back to my slides. We close this. And now I want my presenter view again, please. Presenter view. And this goes here. And this goes there. Perfect. And we even skipped a couple of slides by mistake. Alright, so flat is better than nested. One of the guidelines from the Zen of Python. So what we're going to do is, in order to try and reduce the complexity of our code, we're going to try and get rid of some if statements when we can and when it makes sense. And what we're going to do, the way in which we do that is through what's called a branchless conditional. So an if introduces a branch in your code can branch out into 2 different paths. And what we're going to try to do is get to the same result of what a conditional does, which allows you to do 2 different things based on the context. But instead of using an if, we're going to use some sort of computation to get there. Instead of an if, we just do a computation that emulates the if. Sounds weird, I know. So that's why we're going to take a look at a couple of examples. What does this piece of code do? In English, can anyone describe it to me in a couple of sentences? Exactly, yeah. That's a very good, succinct description. It goes through the iterable. It computes a predicate, so a Boolean function. It checks if the element satisfies a condition, and then it counts the ones that do. Perfect. What I'm going to do now is get rid of the if through a couple of successive modifications that hopefully make sense to you. The first thing I'm going to do is add an else that doesn't change the count. Do we agree that the code still does the exact same thing? I didn't change the behavior of the code. Excellent. Now, I hope you're sitting for this. I'm going to replace the 1 and the 0 by a conversion. So I'm going to take the predicate, the function predicate, and I'm going to use it instead of the 1s and the 0s. Because if the predicate is true, so why am I pointing with my finger? If the predicate is true, then I can convert it to the number 1 with a built-in int. True is 1, and so I add 1 to the count. If I'm inside the else, the predicate is false. So if I convert it to an integer, it gives me 0, and so I add 0 to the count. Do we agree that I did not change the behavior of the code? Okay, now look closely. The if is doing the same thing in both branches. Do both branches look exactly the same? So I don't need the branch at all. So I just got rid of the if by baking the conditional into the integer conversion. Is this something you should do every single day? Of course not. There's a time and a place for everything. This is just I call it quote unquote simple example in the sense that it shows you the mechanism through which this happens. How am I doing for time? Because when I close the slides, sorry, 5 minutes, so right on time. So let's look at another example that looks mechanically different, but it's in the same spirit of let's get rid of if statements through the right computations. Let's write a function, Oxford comma, that takes a list of strings and produces the Oxford comma, the enumeration of those strings in a human readable way that uses the Oxford comma, which is the sneaky comma before the ends when there's 3 or more elements. Let's write a function for this. You're going to start with an empty string that you're going to build up. And if there's more than 1 element, you're going to need to write a list separated, a comma separated. You're going to write the strings with comma separating them. My bad, sorry. Right? So if there's multiple elements, you need to write them out with commas separating them. That's what we have over there. The comma and then the join. of all of the strings but the last one, because the last one is going to have something special attached to it. It might have the and, it might have the comma. If there's 3 or more strings, we need the Oxford comma. If you have 2 or more strings, you need the and at the end. And finally, the last string goes on the end. So we built the string step by step by checking whether or not you needed the different pieces. The long list of comma-separated strings, the Oxford comma, the and the final word. Are you more or less comfortable with this code? Excellent, because I don't have any more time to look at it. So now what we're going to do is we're going to try and shuffle things around. For example, we could leverage identity elements or functions that don't really do anything in certain scenarios, because the first if is completely redundant. Regardless of whether or not you have more than one string, you can just compute the join of the slice. Because if you don't have multiple strings, then the slice is empty. And if you have an empty slice as an argument to join, if this slice is empty, join just produces the empty string. So you don't need the if isn't necessary at all. You can just join the strings. And you could do similar things in some other places. Or you could just literally overhaul the way in which you think about the function. Because instead of thinking the ifs, they mean should I do whatever operation I need? Should I add the Oxford comma? Should I add the final and? Should I use commas to separate words? Instead of thinking about it in this way, you can say, no, I'm going to do the operations. What I need to do is I need to pick the arguments to the functions correctly. I need to make sure that the operation produces the right result. And in doing that, you could think of the function in a slightly different way. Because the result, you can say, look, the result is always the prefix, which is the comma-separated bit, which is typically longer, and then the Oxford comma, which may or may not be there, and then the piece that represents the end, and then the final word. This is what makes up the result. This is the structure of the result. And now what you do is you assign to the variables one at a time. We saw that you can just join regardless of whether there's strings for that or not. And now you could use a conditional expression instead of the full if to determine whether you need the comma or not. Look at the two ends, either the comma or not the comma. The string is there, it's just a different piece of string. Either the end or not. The string with the end or the empty string. Either the last string or nothing, if there's no last string to take at the end. And this just shows you a slightly different structure that's using conditional expressions instead of the conditional statements to branch out. Now, am I cheating a little bit? Absolutely, there's an if there. Can you read the if? The if is still there. But what I want to show you is the different way of thinking about the code, not necessarily the fact that there's no branching here, because there is. It's just inlined. And now for something completely different. Question for you folks. How do you count the number of elements of an iterable that satisfy a given predicate? Does this sound familiar? There was a for loop earlier, but you can actually write it like this. The sum of the predicate of the element for each element in the iterable. The sum is a built-in, right? And what's inside the sum? A generator expression. You don't see there's no explicit parentheses because you can omit them, but that's a generator expression. And what does predicate of element return? Either true or false. So you're using duck typing here because I'm actually adding things up, but I'm adding booleans up. But that's okay because booleans quack like ducks and they look like ducks for the purposes of addition, so I can add them together. Trues stand for ones and falses stand for zeros. What is this on screen? This is my favorite line of Python code. Do I have good taste in Python? It's debatable. This is my favorite line of Python code. It combines three seemingly completely disparate things into one piece of code that has a very clear meaning in English. It counts the number of elements that satisfy a predicate. Do you understand the English? Because if you understand the English, you can kind of understand the code. Eventually, you can get there. And now for something completely different. What's the difference between me and Shakespeare? Why was Shakespeare such a better writer in terms of English than I am. The English language obviously evolved and there's some new vocabulary, but the core vocabulary of the language is mostly the same. The words that Shakespeare knew were mostly the same words that I know. So Shakespeare's edge is not on the vocabulary. It's in the way that Shakespeare combines the words he knows. It's in the way he expresses his ideas. It's in the idioms that he knows, these combinations of words that have specific meanings. And that's what I showed you a couple of slides ago, the sum of the predicates with the generator expression, all of that. That's an idiom. It's a piece of code that has different parts that when put together have a meaning that's greater than the individual pieces. And this is the answer to the question, how do you write good code? Well, the only thing you can do is first write bad code. Take different ideas, try and combine them together, see what comes out of that. Test, play around. Some things will suck, that's the bad code. And sometimes you'll strike gold. You'll find a pattern that you really like. You'll understand an idea that you had never understood before. But you can only get there if first you write bad code. You have to write code. You have to do it. And now for something completely different. If you want to become the smartest Python developer in the room, I write a weekly Python deep dive on my newsletter. Thank you for your attention.